Welcome back to Multigrid Methods. Today we're continuing our journey through analysis on vector spaces and then continuing into a discussion on convex sets and convex functions. I wanted to go back to a topic that we touched on last time, um, and that is the fact that we have this version of Taylor's theorem with remainder. I explained to you that in the simplest case, or maybe a simple case, let's say where f is a function from Rn into R, then this has a fairly simple interpretation. It's going to be f of vector W minus f of vector V is equal to the integral 0 to 1 df. So the derivative of f in this case is just going to be the gradient operator. So gradient of f at the point tw minus 1 minus tv, that's a vector in Rn, dotted with the vector difference w minus v integrated from t equals 0 to 1. That doesn't look like a 1. Now it does. Okay, so that's fine, right? So that's probably a version of Taylor's theorem that you've seen. If you've taken my course on numerical analysis, this is one of those theorems in the back of the book in the appendix, which you can look up. But what I kind of wanted to emphasize that this is an object here that you may never have seen before. And so, what's the problem with this? Well, the problem is that when I calculate this object here, for each t, I get, so remember w and v are fixed, but for each t, that object there is, well, what kind of object is that? That's a Banach spaced object, Banach space valued object. So what the heck does it mean to take an integral of an integrand which has Banach space values? Well, they're built into here. So this all makes sense, but most of you would not seen this sort of thing before. The fact that f is continuously differentiable means that the df is a continuous function. And so this whole object here becomes can be thought of as a Banach space valued function of t. So this integrand we could write as, okay, it's something which takes, to use the notation that we just used a minute ago, it's something that takes a real value t and maps it to g of t, which is in the Banach space y. So that's weird because, okay, t being real valued, that's fine. We can deal with that and think about it. But how do we integrate something which is Banach space valued? Well, the answer is you need this mapping to be what is called strongly measurable. And you need to be able to write simple functions of, or simple function approximations of things which are Banach space valued. That's not hard to do because what I could do is I could build up simple functions based on linear combinations of Banach space valued functions. Um, well, let me not worry too much about that. Um, Suffice it to say that this object is probably something most of you have not seen before, but it still makes perfectly good sense. And the point, I guess, is that I don't want you to worry about the most abstract case where this object here is a Banach space valued function. If you like, just go back to a kind of happier place and a happier time for an easier example. For example, I always will just naturally migrate back to examples like this. And I could even do something a bit more complicated. I could say, okay, well, maybe I want to consider functions from Rn into Rm. Well, in that case, then this is not quite as simple. This becomes a, instead of a gradient, this is what's called a Jacobian. And the thing is a little bit more complicated. And so, you know, the question is, well, what do I do in that case? I don't want you to worry about that. Just think about the simplest possible case where it's a function Rn into R, and then the the gradient is something pretty, or the derivative is something fairly simple that you've seen before called a gradient operator. And then this operation here is the dot product. And so this becomes a real valued function once again. And the fact that it's continuously Fréchet differentiable, means that this operation here or this function here can be thought of as a continuous function, and therefore it's definitely integrable. Okay. So just wanted to bring that to your attention. It's probably something you've never seen before, an integral of a Banach space valued function, but we can make sense of it. These things do exist. We talked about this object last time, what are second derivatives? So we said, okay, well, if the first derivative exists, then that's a mapping. And it's a mapping from a set into a Banach space, right? So, but what is that? What is that Banach space in this case? Well, it's no longer in, and I'm gonna, by the way, we're gonna define the second derivative only for real valued functions, is because, and that is because it becomes, much more complicated to define this in general. It's simpler, and it suffices for our needs to define the second derivative only for functions like that. Well, if the function is real valued, then its first derivative is a function, let's say over a set K, if it's differentiable over a set K, then its derivative is an object that maps K into V prime. In fact, it's a linear function from K into V prime. Now we can ask the question, or actually, I got that wrong. So for each value of each point in K, we get mapped into something V prime, which is a linear operator. In fact, it's in the dual space of V. But this mapping here doesn't have to be linear. Okay, this mapping here does not have to be linear. I'm going to give you an example of this in a moment. Okay, but we can ask the question, is this mapping differentiable? Okay, it's not necessarily linear. In general, it's not linear. But the question there for is, well, can I define a derivative on that? Well, the fact that we defined a derivative in a general setting previously means that we can certainly define the derivative of this operator. We could ask, when is it differentiable? Okay. Remember, we also asked, well, is that mapping continuous, right? It in general, that mapping won't be even continuous, but we can ask the question, is it continuous? And then is that mapping also differentiable? If it is differentiable, then that's going to be an object in this space. It's going to be an object in the space of bounded linear operators from V into this space, which is V prime. Okay, so L of V into V prime. That's if this object is differentiable, then its second derivative has to be from this space. So we said why that has to be the case last time. If it is Fréchet differentiable a second time, then we say, then we call this object a second Fréchet differentiable, and we say that it's twice Fréchet differentiable on that set K. This is always a little bit hard for students to wrap their head around, so it's best to go through an example, and so that's what we're going to do momentarily. All right. Now, if we think about it, let's think about what this object here represents. Let's think about what does an object like this represent? Well, for every v that we pick out, okay, if it's differentiable at a point v, then its second derivative, we said, has to be in this space. Okay, it has to be in this space of linear functionals from v into the dual space of v. All right, well now, if we apply this guy, so let's think about what that does. That means for every v is now fixed. Okay, so now we can apply this guy at some point w1. And then what we know is once I apply it to w1, it's going to be in that space, v prime. So let's do that for just a second. If we take this, okay, and now we're going to apply that to w1. So that gives us an operator which is in this space, v prime. That means I can apply it once more to another operator. Okay, let's use the, or not to another operator, but to another function or another point. Let's call that point w2. Okay, that thing is finally going to be a real number. All right, because this object here is in the dual space. So once we apply that to a w2, that gives us a number in R. But now we step back from this and look at it for just a second, and we realize this looks like it's actually defining an operation on two variables into R. So what kind of operation would that be? It turns out that that's what's called a bilinear operator. A bilinear operator. And so we're going to define this notation to mean exactly this. Okay? So this guy here required us to apply it once more to some point w. Once we did that, then we know that that's going to be a linear functional, which means we can apply it once more to a point w2, say, and finally we get a real number. Well, that means that this object here defines what's called a bilinear form. It's linear in both this point w1 and w2. Well, that says essentially that all second derivatives have this property, that essentially they're just bilinear operators. In fact, it's not just that they're bilinear operators, they're also what we call bounded bilinear operators. So sometimes we have a notation for that which looks something like this. So the set of bilinear operators might be written as chi, chi, and then I'm going to use a separate notation for the target space y. And of course, I could write this as, you could rewrite it as something like chi cross chi, right, into y. So this is the space of what are called bounded bilinear functionals, bounded bilinear operators, I guess. And this is entirely equivalent to, well, actually, in this case, y is going to be the target space, y is R. This space is entirely equivalent to this space, v prime. Actually, I screwed up here because this should just be, we're not using chi's, we're using v's. Okay. It turns out that these two spaces are essentially identifiable with each other. So on one hand, we have bilinear operators into R, bounded bilinear operators into R, and then this weird function space from where we get the normal, where we normally expect the second derivative to exist. Well, if we conclude that this is a bilinear form, then it looks like an inner product, right? Kind of like an inner product. What do we know about inner products? Well, They're bilinear. They have symmetry, right? And they also have something called positivity, which this won't necessarily have. Okay. But, it kind of looks like an inner product, but it's not quite. Okay. But it still begs the question, can I interchange these two W's? In other words, is my bilinear form symmetric? So it's clearly bilinear. The question is, well, can you go one step further and show that it's symmetric? Well, it turns out this is always true. If I have a function from a Hilbert space to R that is twice Fréchet differentiable at a point V, then I always have this symmetry property. And I'll show you an example of that in a minute. Okay, we'll do a computation. I'm going to do the computation on the fly. I haven't done it yet, so I'm going to need you guys to participate with me and keep me honest and make sure I don't make any silly mistakes. Okay, one last topic before we leave this section and move on to the section on convexity. We need to oftentimes characterize the growth of a function. And so we have this notion of what's called coercivity. So a nonlinear functional is called coercive if and only if whenever Vn is a sequence that converges in the Hilbert space norm to infinity, then EVn has to also converge to infinity. So let me give you an example of a functional which is coercive and one which is not coercive. So first of all, a function which looks like the following is going to be coercive. So out here in infinity, it's basically at infinity. And here near the origin, it might wiggle around a bit, might go negative. So let's say, let me get rid of that R and just write X. Okay, so in this case, E of X is a coercive function. As we're going off to infinity, either this direction or this direction, the values of E are going off to infinity. Okay, so that's an example of a function which is coercive. What would be a function which is convex and coercive? And we're going to define convexity momentarily. What would a function that's convex and coercive look like? Well, some of you who know what the definition of convexity is already, you know the answer to this. It'd be a function which looks like that. And remember, for those of you who have seen it before, I'll remind you that a function is convex if and only if every time I take a secant line, then every point on that secant line of the function is above it's basically in the epigraph. It's above the value of the function at that point. So for example, if this is the value of the point of the interpolated point, then the value is above the value of that point. All right, so I'll give you the definition of that in a moment, the exact definition. So we're going to meet functions like that all the time, functions that are both convex and coercive. Could I come up with an example which is convex but not coercive? And the answer is yes. And a good one is the example of an exponential function. For example, let's say an exponential function which looks like that. That's not a good. My hand is getting bumped on the. See if I can do this. Try. Okay, so that's supposed to be an exponential function. So this one's an exponentially decreasing function, and it's exponentially decreasing down to the point 0. So this function is not coercive. However, it is convex. It's convex because if we take a secant line between any 2 points, the secant line lies above the curve of the function, okay, above the graph. Okay, so this function in some sense is good for us in optimization. This function is somehow bad for us in optimization. If we want to do a global, let's, for example, suppose we want to find the global minimum of this function. Here, then we're guaranteed that it's actually going to exist. If the function is smooth, it's coercive, and it's also convex, then we can guarantee that actually you're always going to have one global minimum. But what about a function like this? It is smooth, it is convex, but it's not coercive. And in this case, there is no global minimum. So in some sense, this coercivity is going to be very important to us whenever we're talking about optimization, and in particular, minimization. Okay, so now let's do a little example here, since we've got some time to do that. Let's add a page or two. All right, so let's do an example. So what example should we do? Let's do this one. E of x is equal to, let's do 1/2 x transpose a x. And let's add on to that a little bit. Okay, so the bit I'm going to add on to this is going to be 1/4 sum I equals 1 to m. Now let's do n. Okay, x I to the 4th power. Okay, so there's our function. What kind of function is this? So E is a functional. It takes a Banach space, which in this case is a very simple Banach space, Rn, and it maps it into R. So that's a functional, right? A nonlinear functional. So let's figure out what's the first and second derivatives of this function? What do they look like? So well, I gave a definition of what is the derivative according to, a fairly complicated definition. I'm going to give you a shortcut way of doing this. So you probably all remember how to take a what's called a directional derivative. That's how we're going to calculate derivatives here. So I mean that we're interested in a calculation something like that. So let's plug in for everywhere we see x, let's plug in x plus sy. And then what we're going to do is we're going to take the derivative with respect to s. All right, so let me do that. Take the derivative with respect to s of this object. All right, so we have 1/2 x plus sy transpose a. Now, for the moment, let's just assume that a is, what should we assume about a? A, we'll say, is just a matrix from with n rows and n columns. That's it. Nothing more than that for now. All right, that's good there. And we also have 1/4 sum I equals 1 to n. And this is going to be xi plus syi to the 4th power. All good so far, right? And now let's see, what do we want to do now? So the next thing we want to do is let's calculate this derivative. Now, s is just going to be an element in R. That's it. Okay, an element in R. And so the derivative then is just the ordinary derivative. Well, let's see, how do we do this? Okay, so, well, we could write this object here as a double sum, right? So let's do that before we get into that derivative. That could be useful for us. Sum I equals 1 to n, j equals 1 to n, x I plus SYI. Okay, so now what is the derivative? Or sorry, what does this object look like here? So this we can interpret as a dot product with another vector, right? Because A times X is a vector, and A times X plus SY is also a vector, right? So this just becomes AIJ XJ plus SYJ. Okay, that takes care of that. We still have the derivative to take. And we have 1/4 sum I equals 1 to n. This we can simplify, we can drop the absolute values. xi plus syi to the 4th power. Okay, now I think we can take the derivative. So the derivative is a linear operation, so it's going to pass right through this finite sum, and it's going to see 3 terms, right? But this term is just going to be constant. It sees this term and that term in a product, right? So we have to take the product rule. This term, what about that guy? That one, no product rule. We're just going to pass through there and take the derivative of this. This sees something like a polynomial, right? S to some power. So the power is going to come down, and, well, you know the rest. Okay, so let's calculate that. It's 1/2 sum I equals 1 to n, sum j equals 1 to n. So this is, like I said, the shorthand way of doing this. What happens when we take this derivative of this object? Well, that's a constant with respect to s. And if I take the derivative of this, it only sees the yi. Okay? So I think what we need to do, let's make our lives a little bit easier. Let's say, I can see what's going to happen now. Let's assume that S is a symmetric matrix, right? That will make our life easier because then we're going to be able to make some assumptions. I think that's a reasonable assumption. Okay, so now we take the derivative of that first object. We're just going to get yi aij xj plus syj, right? And now we have to take the second term of that. Let's use, instead, we've already got a curly bracket. Let's use a square bracket. Now let's take the next derivative of that. That's going to be xi plus syi aij times, and this one is just going to be yj, square bracket. All right, let's take the derivative of the next object. Again, derivative passes right through here, and we're going to get 4 times xi plus syi, and then times, right? So, well, to the 3rd power. And then we're going to take the derivative of the thing inside. That just gives us a yi. Okay, so now let's set, well, first of all, let's see, can we simplify this a little bit? So now we've assumed that this is symmetric, so I can interchange the I and J's, right? Interchange the I's and J's, and if I do that, then we see pretty clearly that these two sums are exactly the same thing. Yeah? So this double sum of this and the double sum of this are exactly the same thing, so there's 2 times that sum. There's a half out front which gets eliminated by that, and so the 1/2 goes away. So we just get sum I equals 1 to n, sum j equals 1 to n. Let's see, which way do we want to write it? I think I want to write it as yi first. aij xj plus yj. And then we have a second sum I equals 1 to n. The 4 goes away. 4 cancels with that 4. And we just get xi plus syi cubed yi, right? I can combine this sum as, let's see, I have one big curly bracket, which I don't need anymore, right? I could have dispensed with that curly bracket at that point. Here and here don't need you guys. Now, I have a common factor here, right? And here, I could write this as sum I equals 1 to n of yi times, so what is this object here? So this is just like, that's a matrix, right? Times, well, this is a vector ultimately. So I could just say it's the ith component of a certain vector. So I'm going to write it as the ith component of a certain vector, namely the vector a x plus sy, that vector, and the ith component. Now I can also, let's say, let's use a round bracket now, plus, well, now I don't have to include this second sum because I've taken the sum and this guy out front. And so what's left? What is left is this vector, x, let's see, we can write it like this, x plus sy. Actually, no, that it defies, it's going to defy a simple writing. We're going to have to write it like this, xi plus syi cubed. Okay. Now, finally, to figure out what is the derivative in this case, all we have to do is set s to be equal to 0 in this calculation. Okay, so now let's set s to be equal to 0. E x plus sy. This is what's called the directional derivative calculation. But it turns out, because this is Fréchet differentiable, its directional derivative is always going to exist, and its directional derivative is going to tell us what is the Fréchet derivative. Okay, so s equals 0. Okay, so now what do we get? Whenever we set s equals to 0, then this s goes away here. Okay. S goes away there. And well, this s vanishes, so that whole term vanishes and that whole term vanishes. Okay, so that becomes sum I equals 1 to n yi. Let's see, it is going to be ax ith component plus xi quantity cubed. So this object here defines what is called the gradient of the function. Okay, this tells us what is the derivative of that function. Now, if this nonlinear term wouldn't have been here, let's say that piece there, that or non-quadratic piece wouldn't have been here, then the derivative would have been merely a times x. Okay, we could have said then that the gradient is just going to be essentially equal to that vector. Okay, to that vector. But as it is, it's this whole vector here. That's going to constitute what we call the gradient. Okay. Now we can continue along in this way to calculate the second derivative. Okay. If we calculate the second derivative, what do we get? Well, to calculate the second derivative, you have to take the second derivative here before setting equal to 0. So let's do that by adding another page. So let's calculate the second derivative before we set equals to 0. So ax plus s y. Okay, so that's going to be another derivative added on to the thing we had on the previous page. So let me go grab that. The thing we had before we took or set s to be equal to 0 is this object here. And we're going to copy that and paste it over here. Let's see, I'm going to have to bring that there like that. Okay, let's get rid of that. Okay, so let's continue taking the second derivative. So this is going to be a shorthand way of getting the second derivative calculation. And we have, okay, I equals 1 to n. Okay, the derivative is going to carry into this first in here. See, it sees something which is constant with respect to s, and it doesn't care about anything that has to do with s until it sees this term right here. Okay, and let's see if I can just shorten the calculation a little bit. It's going to be this. Okay, so now what's the next one? So the next one is going to be, let's take the derivative of this term. So we get what? Taking the derivative of this one, we're going to get 3 times xi plus syi squared, and then times the derivative of the thing inside, which is going to be yi. And now to find the second derivative operator, we're going to set s equal to 0, not 1, 0.
Dr. Wise.
Yeah.
So, like that first term, you could split up x and sy, so I don't see how you would get like axi because you can get the ax independent from an s.
Oh, sorry. Should be y,
Okay, thank you.
correct? Okay. Should just be y. And now when we set s equals to 0 there, there's no s terms left, right?
Also, I'm sorry, I think you, with the chain rule, I think it would be yi squared on the second term.
Here.
Yeah, because you have
So
yi
now we're
in
just going to take
front.
the derivative of what's inside.
Yeah, and there was you dropped the yi
Oh,
from.
right. Right. So yi squared, correct. Yep, I lost that one. Are you okay now with that calculation?
Yes.
Are you okay? Okay. So now, now what do I have? I have sum I equals 1 to n yi ay I, which we're going to write in a slightly different fashion in a moment, plus, and then what is this guy's going to? This guy's going to give us 3 x I squared yi squared, correct? So this represents the second derivative operator, okay, the second derivative operator. Now, we said that we should be able to write this as a bilinear form, right? Because so for every x, I forgot to write, so this should be x plus s y. So if I'm correct in my calculation here, we should be able to write this as some sort of bilinear form, right? So I should be able to do that. Let's write this as a secondary sum. So this is going to be sum I equals 1 to n, sum j equals 1 to n. So we have yi, aij, yj. So this is clearly bilinear, okay? And for fixed x, so is the next calculation as well. So this is plus sum I equals 1 to n, 3x I squared. So this is going to be the derivative, or it should be the derivative at the point xi, and it should be represent a bilinear form. So that means, well, in this case, it's a little bit different. It's a little bit different because it is bilinear form, but these two vectors here turn out to be the same in this shortcut hand way, or the shortcut way of doing this. Okay. So from this, I'll leave this as an exercise to you to figure out what is the second derivative in this case. So I claim that it is, well, I'll leave it. I'll simply say I'm going to leave it as an exercise. But this is the shortcut way. I keep wanting to say shorthand and shortcut simultaneously of calculating the derivative and the second derivative operators. The first derivative operator I claim can be found from the previous, nope, not that one. This previous calculation, namely right here. And the second derivative I claim can be found from this calculation, but I'll leave it to you to explore that. All right, so the next topic we want to talk about are convex sets and convex functions. So we already talked about what we mean by a convex set. So a convex set, let's say, well, in R2, is something which looks like this picture. If we have an arbitrary point x and y, then all the points on the connecting line between those 2 points have to be in the set for this set to be a convex set. This generalizes to higher dimensions, and it also generalizes to any Banach space. So that definition, it actually preceded the Taylor theorem that I gave you last time, so I'm not going to go back there. I think you all recall what that is. But we want to now show that a bunch of new sets that we can create, if we assume that the underlying sets are convex, then these new sets will also be convex. So let's start off with this thing called the Minkowski sum. Suppose that X is a vector space and A, B are sets from X. I think once again, I want to say, yeah, let's use subset equal there. So our subsets of X, then the Minkowski sum of these two sets is written A plus B, and it's a set of all points A plus B in X, such that A comes from A and B comes from B. Okay. set of all points A plus B in X such that A comes from A and B comes from B, so-called Minkowski sum. This set doesn't really have a name. It's sometimes called dilation, and it's defined for any lambda in R, and it goes like this. The set lambda times A is equal to lambda A in X for any A in A, right? So this doesn't have to be a positive real number. It could be even a negative real number. This is going to make sense, right? Why does it make sense? Well, because this is a real vector space. I can add any two points from the set or even in the space, and it goes back into the space. And furthermore, I can multiply by, I can do scalar multiplication times any element in the set, and that's also going to be back in the space. So these things, these objects are back in the space, and they're well-defined objects. And we define that to be that new set. Okay, it's in the space X as long as A is in A. The question is, what do you get? What kind of set do you get from that? Well, I claim that if A is a convex set, then lambda A is also going to be convex. Furthermore, if A and B are convex sets, then the Minkowski sum of those is also going to be a convex set. All right. So here's a proposition that, let's see, I don't think, yeah, we're going to prove a couple of them, but we'll prove the first two, I think, as I recall, and leave the latter two as exercises. So let X be a vector space and let A be an index set. And for every alpha in the index set, suppose that K alpha is convex. Then the intersection of all the sets from that index set, or I should say the intersection of all the sets indexed by A, is convex. Now let's suppose that Ki is an increasing family of convex subsets of X. That is, we're going to have this nesting of K1 is a subset of K2, is a subset of K3, etc., all the way up to the last one. Okay, this infinite family of sets is increasing if this happens. If that's the case, then the union over that family of increasing sets is convex as well. And then 3 involves the Minkowski sum, although it's a little bit of a slight extension of the definition of a Minkowski sum. So it involves essentially what are called linear combination of sets. And the idea is, well, if I can define the sum of any two sets, then I can define the sum of 3 sets and 4 sets in the same sort of way. And so this set, if K is a finite family of convex sets, also must be convex. So this is kind of like an extended, again, this is what's called a linear combination of sets, but it's kind of an extension of this dilation plus this definition of the Minkowski sum. 4, let Y be another vector space and let T be linear, but not necessarily bounded mapping. Okay, linear but not necessarily bounded. Now, we don't have any examples of a linear but not necessarily. Well, actually, we do. What is the example of a linear, not necessarily bounded map? The derivative mapping that we discussed earlier is an example like this, okay, of a mapping which is linear but not necessarily bounded. So that doesn't matter too much. It just suffices to say we don't need the boundedness property. And suppose that the set K is convex. Then T of K is as a subset of Y must also be convex. Furthermore, the converse is also true. If TK as a subset of Y is convex, then the set K has to be convex. Okay, if T is linear, so basically what this says is linearity preserves convexity. Linearity preserves convexity. And it's not a hard proof to do. You just use the definition. So that one is left as an exercise. Let's see if we can prove the first two and then see if you can do the latter two. So I hope I can do the first two. They're written here. So let's see if I can remember what's written. So denote by W the intersection of the family of sets and let V and W be in W and T be any number between 0 and 1. Okay, so by the definition of intersection, for every alpha in A, we have V and W in K alpha, right? That's what it means to be in the intersection. V and W must have been in K alpha for every value of alpha. Does that make sense? Now, since K alpha is convex for every alpha, then each one of these guys has to be in K alpha, right? But now we know that each one of these is in K alpha. That means, right, for any T, because each K alpha is convex, therefore, since this is an element of K alpha for every alpha, this must also be an element of the intersection. So that's the proof. Okay, makes sense? It's subtle but simple. Again, suppose V and W are in W, then they must be in there for every alpha. Let T be in any number that you like between 0 and 1. Since we are assuming that K alpha is a convex set, then this point, remember that's the interpolated point between V and W, must also be in K alpha. But if it's in K alpha for every alpha, it has to be in the intersection. Let's see if we can do two, because this one involves unions, but it involves an increasing family of sets. So let V and W be in W, and T be any number between 0 and 1. All right, so to be in this union of sets, then we know the following. There are numbers n, v, and nw in the natural numbers such that v is in k and v and w is in k and w respectively, right? Because of this increasing property. Now let's set n to be equal to the maximum of these two numbers. Since the family of sets is increasing, what do we know? We know that this union of these two sets has to be contained in this, right? Because that's one of the definitions, or that's also a result of the fact that these sets are increasing. Thus, V and W are in Kn, but Kn is a convex set, so this point has to be in Kn. And therefore, this guy, because we're taking a union, implies that TV, or this interpolated point, is also in W. Okay, so again, it's a subtle, this one I think is a little bit more subtle than even one is, but that's the proof. All right, before we state the next result, I want to remind you of something. This one again is maybe a little bit subtle, but so let's see if we can tease it out. What is this little result saying? This result is saying, well, let's go back and recall the definition of strong convergence and weak convergence. We said that strong convergence always implies weak convergence. Strong convergence always implies weak convergence. How do we see that? Well, remember what was the definition of weak convergence? It means that F acting on this difference where F is any functional from this space V prime, the dual space of V, has to go to 0. Okay, so we have to show that this goes to 0 for every possible F in the dual space? Well, we know that the point or the sequence Vn converges to V strongly in the norm, right? That's what strong convergence means in the topology of V. This goes to 0. Now, this is by definition. So remember, I didn't prove it exactly like this, but we proved this with some number m. That was what was called the bound or the bound constant. But it turns out if f is a bounded linear functional, then remember we had this property of matrices that I commonly cite, which says something like this. A times x is less than or equal to the norm of A times the norm of X. Does anyone remember what we called this in linear algebra?
Was that submultiplicativity or the other one?
Consistency.
This one's consistency, yeah. So the submultiplicativity was this one. Okay, which is a slightly related, but in this case, different concept. So it's the consistency which says that this bound up here is actually the norm bound. Okay, so we can replace, instead of just putting a generic, instead of just putting a generic M there, we can replace that with an actual, with the actual norm of the operator. Here, the operator is just the matrix multiplication operator. But in any case, this holds, okay, by virtue of the fact that this is a bounded linear operator, namely a functional in the dual space. All that we need to know is that this is a constant for every fixed f, and the fact that that goes to 0 implies that this has to go to 0. So this shows that if a set is weakly closed, then it's also a closed set. So let me see if I can convince you that this is the case, because you might not have seen this before. We want to show if a set is weakly closed, then it's a closed set. All right. What does it mean to be weakly closed? So it means that it's a set is weakly closed. So first of all, let's remind ourselves, what does it mean for a set to be closed? It means that all the limit points for the set are in the set. So for example, you might have a limit point out here on the boundary. And so we need to know if that's a limit point of a sequence, then that has to also be in the set. Well, if the set is closed, we're going to assume that all the limit points are in there, okay? For example, if this is a disk and we consider the disk with its boundary included, then it's going to be closed. So what does it mean to be weakly closed? It means that same thing, except that the sequence we're going to say, or we're going to talk about what are called weak limit points instead of strong limit points. So we say a set is weakly closed if and only if all of its weak limits are also in the set. Okay, so let's suppose that a set is weakly closed. Well, okay, what does that mean? Again, it means all of the weak limits are in the set. Okay, so now we want to show that if it's weakly closed, then it's closed. Okay, if it's weakly closed, then it's closed. So we want to show that the set K is closed. So start with the set K. We want to show that it's closed. So what we're going to do is we're going to start up by saying, assume that Vn is a sequence in K, and Vn converges to a V, some point V in the space. We want to show V, the point V, is in K, right? But we already know that so this is a limit, it's a strong limit point, right? We know since strong convergence implies weak convergence, we know that Vn converges weakly to V. But since we're assuming that it's weakly closed, right? Since it's weakly closed, V must be in K because we assumed it's weakly closed. But that means that the limit point to this sequence here, the strong limit point, is always going to be in K. So that means that K is closed. So these are the sort of arguments you make in a course on functional analysis, right? Those of you who are taking functional or currently taking 547, you see this all the time, okay? So again, it's subtle. So I hope you didn't miss the point, but if a set is weakly closed, then that set must also be closed, which seems kind of backwards because we said strong convergence implies weak convergence. So we should be able to say that if it's closed, then it's weakly closed. No, it's actually the other way around. Strong convergence implies weak convergence. True. But that allows us to show that if it's weakly closed, then it is closed. The converse, it turns out, is false in general, which is kind of remarkable. So if a set is closed, then it may or may not be weakly closed. However, there's this rather famous result called the Mazur result, which gives a partial converse. If the set is both convex and closed, then it turns out to be weakly closed. So this is going to be a very important point for us in convex analysis. Okay, if a set is convex and closed, then it turns out to be weakly closed. Okay, again, it's kind of, so I'm not going to give a proof for this because it involves pretty deep functional analysis. By the way, has anyone seen this result before? Anybody? Have those of you who are taking functional, have you seen it?
I think so.
You have, okay. Okay. All right. So let's see, why am I not? There we go. All right, so now convex functionals. So this one, this definition here is analogous to the picture that I drew previously. Okay, so we say a functional, nonlinear functional from a Hilbert space into R is convex if and only if so this is going to be the secant line is above the curve. Okay, the secant line is above the curve. If that happens with the inequality like this, then we say that it's merely convex. However, if this inequality is strict, then we say that the curve or the function is strictly convex. So let me give you a picture of both examples, maybe. So we've already exhibited a convex function before, and I think it's something you've probably all seen before, something like that. So I'm going to give you first an example of a strictly convex function, and then let's see if we can find an example of a function which is not necessarily strictly convex. Okay, so let's draw the secant line. Secant line is like that. Okay, so now this would be on the bottom here. Let's put the corresponding points. This might be V, and this would be W. Now, of course, we have to pretend along the bottom this is the Hilbert space. And along this axis is E. Okay? So now if we pick a T between 0 and 1 and interpolate between V and W, that's going to give us a point, for example, like here, let's make that purple. Okay, purple point. So this point here is going to be T V plus 1 minus T times W right there. Okay, so let's locate that point on the secant line. On the secant line, that's precisely going to be that point. And on the curve, it's going to be this point. So the question is, for every such points, for every one for all such points where t is between 0 and 1, is the point on the secant line strictly above the point on the curve? And the answer is yes. For a function which looks like this, it's always the case. And so in this case, we say that the function is going to be strictly convex. So let's give an example of a function which is not necessarily strictly convex, but merely convex. Merely convex. What would a function like that look like? Well, maybe something like this, right? So it's coming down here, and then we're going to join that with a straight line. So is a function like that strictly convex or merely convex? And I say in this case, it's merely convex. If I draw a secant line for this function, then we might do well to pick one there, but that's not the only kind of secant line I could choose, right? I could draw a secant line at this point, from that point to that point. And clearly that one is not strictly above the curve, right? For that particular secant line, I don't get a strict inequality, I merely get equality. So this guy over here, at least it appears, is strictly convex, but this one is merely convex. Okay, I hope everyone gets the concept. Now I can draw pictures with this one because this is such a simple function. This is a function from a Hilbert space into the real line. What if this was not the real line? What if it was just another Banach space? Well, the problem there would be I might not be able to put an ordering on that Banach space. So we really need this to be R so that I can have an ordering. Okay, I can use the less than or equal symbol. All right. Last couple of let's see, slides. I guess I probably won't get into this one. Let's do this example though. So the following are examples of convex functionals. So if V is a Hilbert space, then it turns out that the norm is convex. The easiest way to see that is, well, we could draw this in higher dimensions, but basically the picture always looks like this. What does the norm look like if the Hilbert space is R? Okay, the real line. The norm is just going to be this function like that. It's just going to be the absolute value function. And so I claim in hyper dimensions, the picture is more or less the same. And this function is strictly well, not strictly convex, it's merely convex. That's because if I draw a secant line, let's say on this branch here, right, then the points in the secant line lie on the curve. So it's not strictly convex. What about this guy here, this function? Well, this is the function I was playing around with just a minute ago. I was trying to show you how to calculate the derivative and the second derivative for something which looks like this. I said it makes life a lot easier if we can assume that A is symmetric. If we assume that A is symmetric positive semi-definite, then this function here, it doesn't take too much to show, is actually merely convex. If that matrix is, however, strictly symmetric positive definite, okay, so not positive semi-definite, but positive definite, then this function is strictly convex. And finally, this function, which you may or may not have seen before, is what's called a support function. We're a little bit over time, so I may just start with this one next time, and I'll draw a picture for this one. So I'll end there, and I apologize for being just a little bit over, and I'll take your questions.